Hi guys, welcome to Learn Electronics Repair. I have some PCBs here from PCBWay who are kindly sponsoring this video. This is one of their shared projects I will show you in a moment on the PCBWay website. And this project is a simple USB load. According to the documentation, this should allow you to put a load up to 35 watts on a USB port, fully variable with the potentiometer. So let's take a look at this project on PCBWay's website and then let's talk about what we're going to do today with it. Here is the project. On PCBWay.com you will find a large shared project section, so you can find here all sorts of projects. These are things that people have designed, created the PCB design and uploaded them to PCBWay. So you can order PCBs from here. Generally speaking, 5 PCBs will cost you less than $10, including postage, and you can build these projects. There are so many, it's impossible to go through them all, and there are more and more being added all the time. We could just click on one at random, so BQ test board, a way to test the resistor programming for a BQ25570 energy harvesting board, whatever one of those is. So with all these projects, these are things that people have designed, uploaded the project onto PCBWay, and if anybody orders any of the PCBs, the designer, as it says here, PCBWay will donate 10% of the cost to the author. So the author gets a commission. And that's great because you can upload as many projects as you like and you don't have to spend any money stocking these and worry about shipping them out. All that is done for you. You get a commission. You can order a few for yourself so you can test your project. If you need to, you can modify it, and when you're happy with the finalized design, you can publish it on here. So here is the particular project we're going to look at today. DIY USB load tester, 35 watt using TIP122 transistor. And normally on here you will find the Gerber files, so you can download them or you can order the PCBs. You may find the schematic, but that all depends on the author, what they wanted to upload. So with this project, we simply get a link on YouTube. And if we look at the link, once we get past the advertising, of course, you will find in this one, it's a very simple video. There's no speaking, they're just showing you the device, showing you the components you need. I will link this in the description. This is just the components you need. And then they are showing the load tester in action, so here we can see it. Okay, I was looking through the comments. Somebody is asking for the circuit diagrams, but he never gives a link. So we have the PCBs here, but we don't have a circuit diagram. Circuit diagram please, 2 replies. He gives a link here, but that's just straight to PCBWay's website. And on here, I can't find the diagram. So what I will do, I will post the link to this project for you guys in case you're interested. We will build one. Let's put one of these together. We can give it a go. I'm fairly confident we'll need some sort of heat sink on the transistor to make it work properly. And then let's reverse engineer it. It's quite simple. Let's create our own schematic. And then maybe we can design a variation on this which has a proper heatsink. I was reading through the comments on this guy's YouTube channel. EasyOne, his channel is called. Credit where credit is due. This is the guy who uploaded the project. And somebody was saying that you don't need all of the schematic effects, so they say you can just do it with the transistor with 10k parts, but fair enough. And he says he has 4 transistors in parallel. to have 100 watts. Okay, so I think what we can probably do is look at something like that, put a little heatsink with fan on this. We can make space for up to 4 transistors, and then you can populate them as you wish. And we'll have an updated schematic, and we'll have an updated PCB. I can then upload the PCB to PCBWay, and there's another project for you guys. Referring to the video I was just showing you, and I'm going to link, we can see that basically this has a TL431, this is a voltage reference, LM358 dual op amp, this is the transistor. We have a few resistors, 1, 2, 3, 4, 5, 6, 7, they're all marked quite nicely. These marked 104, 104, 103 are ceramic capacitors. This is where we connect our USB plug, and this is where we connect our potentiometer. So I'll put one of these very simple PCBs together. Now let's try it. I've assembled the PCB. It was quite simple. There is one resistor on the back down there, the surface mount one, 0.05 ohms. That is the current sensing resistor. And there we have it. So let's test this. We'll connect it to the little USB analyzer I now have. I'll connect this to my power supply. This is my 65 watt. Now let's see what it does. Okay. Plug in, switch on, starting up. Oh, and it's drawing 1.18 amps. So let's just, and I can adjust it. Okay. I think that's the maximum for my power supply, but I looked at it at this voltage. Okay. So you can see at the bottom the wattage. Let's set it to about 5 watts. Okay. And let's see if the transistor is getting hot. I could risk my finger, but I'm going to use a thermal camera just to see. It's been on for a few minutes now, as you can see. I'm just getting my phone ready with the camera. Okay. So let's have a look at what we have. So you can see there it is getting hot. I have to zoom the camera out a little bit actually so you can see. Okay, and you can see that is getting hot. I'll just put the thermometer on. So from here I can see about 50 degrees. Let's turn it over so we can see the actual transistor. You'll notice I've mounted mine on the back of the heatsink. And that's at about 60 degrees, 58, okay? 59 degrees. Let's turn the load up a little bit. So it's about 10 watts now, okay? What's it doing now? Well, it is about 70 degrees. So it's getting quite warm, 71, 72, it's still heating up, okay, 73. So it's, as you might expect, getting quite warm on that heatsink, which is quite small. But you'll see that the transistor is getting hot much more so than the heatsink is. So let's put some thermal compound on. It's just bolted to it at the moment. I'm sure you can see the whole heatsink now, so the heatsink is quite cold, yeah? Let's put some thermal compound on it. Okay, you can see I put some thermal compound on that now and bolted it back on. It is still quite hot actually. Let's put this back on again. So we'll connect it once more to our analyzer. Okay, switch the power supply back on. About 10 watt, just under. Let's see how warm it's getting now and if it's distributing the heat more. Okay, so you can see it there. Once again, I'll put the thermometer on. So it's reading about 73 now, so it has cooled down a little bit. It's clearly transferring more heat into the heatsink, but not particularly efficiently, okay. 78 degrees. 80. So the load clearly works, but this is not going to handle 35 watts. The maximum I can actually get it up to is about 14 anyway. At this voltage, you can see the voltage is dropping. That's on my cable, no doubt. Okay. What I can try is bolting a transistor onto this. So this is off an old graphics card, you can see. I can connect my bench power supply and power the fan. I have some holes in the corners. I can use one of them for now. So I'll fit a transistor on here. Let's see how well that works. Okay guys, so I've effectively fixed it to the heatsink via one of the existing screw holes. It's off to one side, but I've put some heatsink compound under it. The fan's running from my bench power supply. So let's see what this actually does. I'll just put something under here so it can't short out. Okay. And there you can see, so 5 watts. We'll increase the load to just over 10 watts again. And let's see what temperature we're getting now out of the transistor, if we can see in the right direction, okay? Well, that's where the transistor is, and that's reading 42. That's actually the transistor through the board. Okay. Probably can't easily get down there, not how you guys can see it. 47, 48. And it's obviously spreading the heat out much better now, yeah, you can see that. So, I think there's some mileage out of this project, guys. What we probably want to do is to use 2 or more transistors on one heatsink to spread out the load between them, and then we can probably get 30 or 40 watts out of this. I don't think we'll do it out of one transistor. I think it's a little bit ambitious, but the thing does work, yeah, and it's quite simple. As I mentioned earlier, one of the comments on the original video, somebody said that they put 4 of the transistors, the output transistors, the TIP122, in parallel and built a unit that could dissipate 100 watts, okay? But although the guy said he put the transistors in parallel, he probably didn't exactly. You might wonder, actually, can you put transistors in parallel to effectively 2 of them to double the current and the wattage dissipation? So what you're probably thinking is that you can take a transistor like this. Okay. It's an NPN transistor. Some sort of load. Okay. Ground. You have something driving it on the base. And then just effectively take another one. So from here, connect another transistor, same type if you like, why not? Okay. And then from the base to here. So we've wired the 2 transistors in parallel. Can we now handle twice the current? Well, maybe we can and maybe we can't, but probably this is not a very good way to do this. And the reason is that the current flowing through the transistor collected to emitter, that's the current flowing through the load, will depend on the current that's flowing from the base to emitter. And the current that's flowing base to emitter will depend on the actual voltage difference between the base and the emitter. So you may think that if you have, for example, 0.60 volts on the base compared to the emitter is 0, and we have the same on this one, they're connected together, that the 2 transistors will conduct evenly. But unfortunately, everything that's built has a tolerance. So you may find, for example, that this one actually turns on at 0.595 volts, and this one not till 0.600 volts. And you may think, well, that doesn't make much difference. But what will happen is, once this one starts conducting, the voltage across the base emitter will settle at 0.595 volts, and it will never get to 0.6. Yeah, so this one will be handling the load and this one won't. So you could have a situation where one is actually passing all the current, the other one's passing none. Now, it's not quite as black and white as that. So what you'll probably find is that one is passing more current than the other. They're not evenly distributing the load. The way around that, basically, is to take the same sort of circuit we just had. Load, okay. One transistor to ground, okay, through a resistor. And the other transistor you can put here. And instead of connecting the base to that base, you effectively have another resistor, and this is coming from whatever circuit is driving this. Okay, so what will happen is now effectively the base of this one could be at 0.595 and the base of this one could be at 0.600 because they're coming through two separate resistors. Okay, so that will alleviate to a fair extent this problem. It's more normal actually, you'll find, that you will not have the emitters connected like this either. So what you'll have to have your transistor in parallel, this is your load, okay, this is one transistor with a resistor in the emitter to ground. This is your other transistor, which also has another resistor in the emitter to ground. Yeah, like so. And then each will have, as I said before, its own base resistor. Driven from whatever the source is. So that's how you would normally do it. Now, these resistors would normally be very low value. If this was an audio amplifier type circuit, these will probably be like 0.22 ohms or something like that. And these will be larger, but not that much larger. It depends on the gain of the transistor. It might be 20 ohms or something like that. But our transistors are not normal transistors like this. Our transistors are Darlington transistors. So with your Darlington transistor, you have this setup. Okay. Sorry, it was behind the inset picture. Okay. So you have this type of setup, and this increases the gain. So in actual fact, when you have transistors like this, especially power transistors, you might find that the current flowing through here is 10 times or 15 times the base current. So effectively, if you have like 15 amps flowing through that way, you're going to have about 1 amp flowing in this way. With a Darlington, because it's very high gain, that doesn't happen. You don't have a very high base current. So if we look at our circuit, and we'll see, I'll just get it where you can see it. This is the output transistor, this is the base, okay? And the base, if we look at it, I've been just drawing on this one previously, has a connection to here, okay? And this is a 1K resistor to here, and the other end of that goes to pin 1 on our chip, which is the output of one of the op amps that are in there. So our circuit, the output transistor is being driven by a 1K resistor, or via a 1K resistor, I should say. I'm actually not going to put these two low value resistors in, at least initially. Let's see how well it works. What I'm going to do is take another 1K resistor and drive the base of the other transistor, which I'm going to put in parallel. So we'll have one mounted here, one mounted here, collector and emitter in parallel, put the base on their own resistor individually to pin 1 on the chip. This is the effectively output of the op amp, inputs on 2 and 3. Okay, so let's try it and let's see using the thermal camera how well these two transistors actually share the load, because we can assume pretty well that if one is getting much hotter than the other, it's not balanced. Okay, I have it all connected up, ready to go. Now you may be thinking, and you will be right if you are thinking this, that if I put two 1K resistors, one onto each of the bases of these transistors, I will effectively double the current that this chip has to provide to drive the transistors. And that actually is correct. Now, you could, if you wanted to, and if you were designing this rather than kind of like experimenting as I'm doing, you may want to work out using Ohm's law the maximum current that can flow into the base of each transistor, and then have a look at the data sheet for this chip, LM358, and see how much current it can provide on the output, and then work out if there's going to be a problem. The other way you could do this, if you like, is just to try it, and if we want to, we can measure the voltage drop across the base resistor. That will basically allow us to calculate the current that's flowing, and we can do it on both of them and see if we have the same current in both as well, actually. So let's connect this back up again and let's give it a go. And then let's take some measurements. So I will switch on. Okay. And we have 8 watts at the moment. So I'm going to turn it down a bit. Okay. We can turn it up towards the maximum. About 16 watts is the maximum we can get out of it. Let's turn it down to about 4 watts. Now let's make some measurements as I just mentioned. Okay, so there's the multimeter. I'm on volts range. What's the voltage drop across our resistors? Let's have a look. Just goes kind of half to sleep, don't worry about it. So this resistor has 0.235, okay? And this one has 0.244. So you can see there's a slight difference in the base drive on each of our transistors, okay? 234, 244. So there is a small difference, and from that we can calculate the current. We know the resistance, we know the voltage, we can work out the current into the base. So let's do it. So we have 0.234 and we have 0.244 volts, okay? Now current, Ohm's law, VIR. If we want to know the current, it's V over R. So for one of them, it's 0.234 divided by 1,000. Another one is 0.244 divided by 1,000. But we don't know exactly if our two resistors are the same value because they will have a tolerance. Let's see if we can measure them while they're in circuit. So this one was reading 0.234. It's reading 881 ohms. And this one is reading 883 ohms. So they are actually extremely close, okay? 881, 883. So let's do the calculation based on the fact they are equal effectively, okay? I'll base it on 1,000. We're reading 883. In fact, no, let's base it on what we're seeing, but it may not be that actually if I measure them out of circuit, okay? So let's see what we get. Oops, I'm sorry guys, I'm slightly off the shot. And I know you don't like maths, but sometimes this is fun, yeah? So one of them is 0.234 divided by 883. So you can see that current is extremely low. It's like 26 microamps, okay? Say 26.5 microamps. What's the other one? I bet there's not much difference. Divided by 883. Equals, yeah, 27.6 microamps. So we know the current is extremely small, and that's because these are Darlington transistors, and we know that they're basically equal. Let's look at them with the thermal camera. We'll switch back on again, and we'll turn the load up somewhat, yeah. So let's turn these up towards the maximum. 16 watts, okay? Let's have our transistors. So I'll put the temperature reading on. I don't have the fan running at the moment, by the way. Okay, so this transistor is running at about 41 degrees. And this one is running at about 38.5, okay? So 38.5, 41. So that's very happily handling that load, okay? Without the fan, it's just tepid, yeah, it's just tepid. So obviously it will warm up, we need to have the fan running, but that's what we have. It's been a little while now. This one's 39, and this one is about the same, okay. So they're obviously balanced quite nicely. And there we have it, guys. So these PCBs are very good, actually. This is a very handy little load. It works better with the two transistors that we've just seen. So let's think what we're going to do next. I did mention at the start of this video about creating another PCB, and on part 2 that's what we're going to do. So we're actually going to reverse engineer this to work out the schematic. I'll make a little video actually about that, because if you want to learn how to make a PCB into a schematic, something like this is the best thing to practice on, because it's not too complicated, but it's actually probably more complicated than you think when you come to do it. So we're going to recreate the schematic from this, and then we're going to modify that to handle up to 4 transistors and make the circuit board a bit wider so it can fit directly onto the back of something like this heatsink. I mean, these are off an old GT series graphics card. You can probably pick these up for next to nothing, especially faulty ones or even working ones. And this is an ideal sort of heatsink for this, and it's cheaper than buying a new heatsink and fan, even if you buy a little graphics card and you don't use it, yeah? So let's make the PCB to fit nicely onto one of these with the 4 transistors, so effectively the whole thing will bolt down, yeah? So that's next month. Now, PCBWay, and thanks PCBWay, by the way, for sponsoring this channel. You allow me to do this sort of thing, yeah, which I really enjoy. I know a lot of you guys enjoy watching, so big thanks to PCBWay. I always make 2 videos a month for PCBWay, so one of them will be the continuation of this project, and the other one will be the continuation of the 30 volt 10 amp power supply project, okay? So during March, one I normally release around the 10th of the month, and the other one around the 20th of the month, give or take a few days, okay? So put those in your diary if you're interested in either of those projects, and we will carry on with both of these. Okay, hope you enjoyed that, guys. Last time, big thumbs up to PCBWay, and I'll see you all soon on another Learning Electronics Repair video. Ciao for now, guys.